Okay, thank you. Good afternoon. It seems that we have people in the waiting room, so we will start. As I said at the beginning, thank you. Good afternoon, and thank you for joining us in this new webinar organized by the Autonomous Surface Ships Committee as part of the Spanish Association of Naval Architects and Marine and Ocean Engineers. Today is the second webinar that we organize around the autonomous surface ships, and we will dedicate the session today to real cases of this type of vessels. This committee is part of the technology area of the association. So thank you for the team that is running this effort, and I'm sure that you will share very interesting cases from different countries and different entities, European countries and entities, to explain where we are in the state of the art with real cases. So with no more delay, I will pass the stage to Javier Palmies, who will lead the session. Thank you very much for joining. Enjoy. Thank you. Javier?
Hi, good afternoon. Many thanks to everybody, and especially to the speakers that are the most important part of this session. Well, we will start with the first conference that will be done by Lars Andreas Wenenfels. He's a research scientist of SINTEF Ocean in Norway. His primary research focus on how we can realize autonomous shipping and how we measure the impact that this technology has on safety, economy, and society when applied to waterborne transportation of people and goods. He has experience with third-party HIL verification of maritime control system software, as well as technical project management and engineering of power, propulsion, and automation systems on several ships. Lars graduated from the Norwegian University of Science and Technology in 2009 and holds a Master in Engineering Cybernetics. And he will be talking about the redesign of waterborne logistics with a view to the future technology development for mass. So I will leave you, Lars, with you, that for sure that this session will be very interesting. Okay, Lars, go ahead.
Thank you very much. Just to confirm that you can see my monitor.
Yes.
Okay. Yeah. Thank you very much.
Okay.
So thank you very much for that introduction, and it's very nice to be here today. Which I will use some time to speak about some of the content that we do research on in European research projects. Myself through SINTEF Ocean. So we will have a little bit of a look at some of the future developments of autonomous ships with respect to the technology itself, and which furthermore can be used to create new vessel concepts and redesign of waterborne transport systems or logistics. So a common denominator for a lot of these European projects is that they investigate how we can use highly automated ships in order to shift a significant amount of freight and cargo transport from European roads to multimodal transport solutions. And why is that important? It is important because shipping is the most sustainable form of transportation of cargo, whereas trucks are the least sustainable form of transportation. Yet, truck transportation is increasing relatively to shipping. So in response to this, I would like to use this presentation to argue a couple of main points. The first is that so-called small uncrewed vessels can improve or can contribute to improved waterborne logistics by increasing the competitiveness of shipping. And a second point is that the realization of this competitiveness for the vessels depend on our ability to design safe and efficient human automation interfaces. So truck transportation is increasing, but emerging technologies gives us alternatives. Normally, we would use a big ship to transport, for example, a large amount of containers between European cities. And then we would use trucks for last mile transportations to end users. What if we, instead of trucks, introduce smaller feeder ships that could visit very small coastal ports and transport the containers even further into the hinterland? This is the case of one of our project scenarios that we investigate. The big ship would still bring many containers between ports or terminals, but the smaller ship would bring a few containers from one of these terminals to several small local ports. And what you see here is an example where the main liner ship, big ship, go along the coast of Norway, whereas this small ship goes into small rural ports in a fjord in Norway. But the concept is applicable to several other places within Europe. So the main idea with such a system is that the small ship can bring cargo much closer to end destinations compared to the big ships, and we can reduce the number of port calls for the bigger ships. Then we can perhaps also reduce the need for last mile transport on roads. However, to make this transport case viable, one of our conclusions is that the small feeder vessels should be uncrewed or unmanned. And why is that? This leads back to the basic question on why we're interested in autonomous ships for cargo transport. A main reason for this is that autonomy can make shipping more competitive, and the increased competitiveness can mainly be attributed to the vessel being uncrewed. If we move the crew to shore, we can remove, for example, the accommodation and those areas that we normally use for crew, and this makes it possible to carry more cargo and reduce power consumption. We can, for example, also remove a range of equipment, such as crew safety equipment, and it also means that we can remove all onboard crew-related costs. And these, let's say, rather radical changes allows us both to rethink the ship design itself, but it also allows us to rethink the transport system concepts that the ships are part of. And this is some of the background for why we investigate how uncrewed or unmanned ships can improve waterborne transport systems. If we find the good cases, then we can improve the efficiency to make ships compete with trucks, both on cost, but also on flexibility. So we say that the feeder vessels should be uncrewed, but they will still depend on humans. And how is it that the ships are uncrewed, but still will depend on humans for day-to-day operations? One example is that it is difficult to automate all forms of ship operations. So we would have to have a remote control center or a remote operation center with operators that have to assist the ship. In fact, it might not be cost effective, and it might be too demanding of us to require technology to solve all ship functions. Consider, for example, a mixed traffic scenario where an uncrewed ship needs to be needs to interact with one or more conventional uncrewed ships. The uncrewed ship might be unable to interpret the actions planned by the conventional ship and will need help from humans to plan its next move. In this case, humans need to be in the loop to handle complex or unexpected problems that arise. So, we are not talking about a single vessel or a single ship anymore, but rather a ship system where we have several actors. We have the ship, we have the control and automation systems on the ship and in the remote control center. We have humans, we have support systems. This could be local sensor systems placed on shore. It could be planned response services, and it could also be, for example, automated mooring or automated cargo handling in the ports or terminals. This means that it means that it's perhaps counterintuitive that the small feeder vessel needs to be uncrewed to be competitive, but that uncrewed ships needs humans in a remote control center to function. So how can we do this? We cannot simply move the crew on a traditional ship one-to-one from the ship to the remote control center. That would not give the cost savings we need. Instead, we need to find, let's say, the amount of control center operators that makes the transport system competitive, and at the same time ensure that the ship automation systems, together with humans in the control center, can cooperate to ensure safe operations. And this will require what we call a proper design of the human automation interfaces. And we know that both, let's say, the role of the remote operation center or the remote control center and the role of the humans in an autonomous ship system still is unclear. And this is debated also on IMO level and in several nations, and also within the European Union. But I think we can still define some high-level requirements to what we should expect from the automation systems on ships and what we should expect from the humans in the control center. So basically, when automation and humans must cooperate, both can be in control of the ship, but only one at a time. This means that when automation is in control, it must be in control. But we must be able to safely hand over control to the automation system. And when we do so, we need to trust that automation will do its job that we designed it to do. So let us revisit the case of the mixed traffic situation, where our uncrewed ship do not understand how to proceed when it meets a conventional ship. So what we require then would be that automation system on the ship should detect this scenario and send a request for intervention to the operator in the remote control center. In addition, we expect that the automation system informs the operator about the response deadline. The operator would then have to respond to the request for information, gain situational awareness, and then act appropriately before the response deadline expires. And this is, in fact, a representation of what we call constrained autonomy. If we generalize this situation to all processes and functions of the ship, then constrained autonomy could mean that the automation system detects when its capabilities are out of boundary, then proceeds to request information with a response deadline that is greater than the maximum response time of the operator. And this could also be a requirement for safe operation. So if you manage to design such a system at this maturity level, then each operator does not need to follow a specific vessel actively in the remote control center, but could follow a fleet of vessels passively and be informed when intervention is needed. So we minimize the need for operators, we maintain safe operations, and we provide an efficient alternative to transportation of goods using small uncrewed feeder vessels in combination with normal short-sea shipping ships. It remains, though, to design and both verify automation systems that are capable of this, and we still need a better understanding of operator response times in various scenarios. So, within one of the ongoing EU projects, the AutoShip project, we have recently published a roadmap for autonomous ship adoption and development related to cargo transportation. So within this roadmap, we have done a systematic classification of the key enabling technologies that we require from us and what we consider as realistic technology development steps for each of these technologies. And as you can see within the red box, this is the constrained autonomy technology development level that I've been talking about today. But we also have, for example, what we call automatic operation level, meaning that you have a system where automation are carrying out processes on the ship, but needs continuous supervision from humans on board the ship. Then we have the remote control development steps, which is basically the same as automatic operations, only that we move the crew from the ship to remote control centers. In addition to the constrained autonomous development step, we have also discussed a little bit something about what we call a standard RCC constrained autonomy. And we think that this is a step where the interfaces between the remote control centers and constrained and ships are to a high degree standardized, so that it's possible to have big scale, let's say, changes between ship and control centers worldwide. And finally, we have also discussed what we call full autonomy. And I will show on the next slide that we have based this, we have combined a little bit this technology development steps with the ships and operational concepts. And the small red square is what I've talked about today. It's so-called sheltered water shuttles, where we have operation in national waters with constrained autonomy technological development step. And there are a lot of others combinations of ship and operational concepts with autonomous technology development steps, and together with the main constraining factors that let's say makes a landscape which is very interesting when we consider how to utilize this technology for future waterborne logistics and transport. So for those of you who are more interested in what we have said in this roadmap, feel free to download the roadmap on Autoship project or contact me later. So the Autoship project has been, let's say, a project where much of the focus has been on ship technology. But we also work in several projects that consider how to apply this technology into the logistics systems, both for short sea shipping, not so much for deep sea shipping, but also for inland waterways. And one of the things that we see is that in order to be able to let's say, improve the efficiency and competitiveness of waterborne transport, we also need to look into ports and terminals. So one of the upcoming reports that we will have in the Aegis project, which is supplementary to the Autoship project, is a roadmap that builds on the technology, automation and autonomy technology development steps, and puts them into several more specific logistics scenario and transport scenarios with port developments, and we try then to explain what should be the direction in the upcoming future. And this is something that we also build on in new research projects. For example, the new project, this is mainly focused on inland waterways, but we have major issues with how to have resilient transport systems, and we then investigate how autonomous inland navigation barges can contribute to that, in addition to zero emission transport. And the same with what we call the Seamless Horizon Europe project, where the objective is to create a library, let's say a library of technology solutions, which are building blocks for highly automated short sea ships. So to conclude this presentation, I would like to round off with a couple of main points that I highlighted in the beginning of this presentation. Small uncrewed vessels can contribute to improved waterborne logistics by increasing the competitiveness of shipping. But in order to do that, we need to focus in the future on proper design of human automation interfaces that supports constrained autonomy, and that could lead to a reduced need for remote control center operators per ship, and again support the case of making uncrewed feeder ships competitive. So that was what I would like to say today, and with that to say thank you for your attention, and yeah, back to you. Thank you.
Okay, thank you very much, Lars. Well, I forget at the beginning to tell that please, all the questions you have, please send it by the chat, and we will go on the question and answers at the end of the session. Okay, next will be Andy Stanford Clark. Andy is an innovation leader in IBM research and is a technical leader for the Mayflower Autonomous Ship project. He is an IBM Distinguished Engineer and a master inventor with more than 40 patents. Andy is based in the UK and has been working in the area we now call the Internet of Things for more than 25 years. He is a researcher in computing and mathematics and physical doctor in computer science. He is a visiting professor at 3 UK universities and fellow of the British Computer Society. He will be talking to us about the Mayflower autonomous ship. So, Andy, go ahead.
Thank you, Javier.
Welcome.
Okay, can you see us okay?
Yes, okay.
Okay, so really interesting to follow on from Lars's presentation because I had lots of resonance with what he was talking about. So this is the Mayflower autonomous ship. This is a 3D photogrammetry scan that we had done of it, so we can twirl this around in 3 dimensions in a Oculus headset and dive inside the ship and discuss maintenance plans with the crew and with the team using that data. So the idea of Mayflower autonomous ship came from the city of Plymouth in the UK was trying to decide how to celebrate the 400th anniversary of the original Mayflower crossing the Atlantic in 1620, 403 years ago now. And some people wanted to build a wooden replica of Mayflower, and somebody pointed out that had already been done. And a guy called Brett Phaneuf, who's the owner of what turned out to be Mayflower, said, well, why not, instead of looking backwards at the last 400 years of maritime history, why not look forward to the next 400 years and build an autonomous ship that can sail itself across the Atlantic, recreating the journey of the original Mayflower? And they said, go on then. So he said, right, I will. So he did. So with some funding from the not-for-profit marine organization Promari, he built this ship, and IBM is the technology partner. So there's a lot of IBM technology inside the AI captain, which controls the Mayflower ship. But the primary purpose is to be a platform for scientific research. So she has experiments on board, and with a view to improving our understanding of the impact of climate change on the ocean, and also the effect of man's pollution on on the ocean, particularly of microplastics. So it's all very sort of geared towards climate research and oceanographic research. In control of the ship is an AI captain, and just referring back to Lars's last but one slide, this is full autonomy, so all level 4 autonomy. So the AI captain is in full control of the ship. It's human on the loop rather than human in the loop. So the AI captain tells us what it's done rather than asks us for permission. And there's no notion of handing over back to the human operators, because although we are watching it, we don't consider ourselves to be the operators of it. We can intervene in emergencies, but the AI captain is formally, legally in command of the ship. Once you've decided to have an unmanned ship, again, as Lars was saying, you get rid of all sorts of costs and space considerations, and the shape of the ship, form follows function. So we don't need sleeping quarters, galley, toilets, fresh water, storage space, headroom, all that goes out the window. And we can dedicate the entire space to the purpose of the ship, which is to house the scientific experiments. And these bays that you can see marked off with the brackets allow us to put a different research experiments in for different missions, and we can swap them out fairly readily between missions. So the ship is largely solar powered. You can probably see on this other slide, it's got solar panels on the top, but there's not quite enough room, not enough power coming from the solar panel, so there's a biodiesel generator to help when there's not enough power from the sun. That powers an electric motor which turns the propeller, and then there's quite a lot of IT equipment on board, forming the brain of the AI captain. Now we talk about AI in the AI captain, but actually it's an interesting combination of deep learning, as we would know, sort of machine learning and AI in a traditional sense. And then we've got prescriptive logic or rules-based systems. And we've got a linear programming optimizer as well. So those three things together work in conjunction to form the brain of the AI captain. And this idea, if you've played with ChatGPT, you'll know that it sometimes hallucinates or daydreams, as people generously say, or makes crap up, just makes up rubbish sometimes. Having a rules-based system in front of an AI system can keep the AI sort of honest and make sure that it doesn't break any rules. And we found this is a very powerful model, both in the marine sector for AI captain, but also in other applications as well. And the way this all works is that we use machine learning to do image processing using an IBM product called Maximo Visual Inspection, part of our Maximo asset management suite. That has been trained on captioned images, about 1.5 million images from the ocean, things we might see, everything from cliffs to icebergs to ships in different rotations, to seagulls, to stand-up paddleboards, to canoes, whatever we might find. And so it knows, it has a situational awareness using 6 cameras around it, 2 at the front, 2 at the back, 1 each side. That visual data is augmented or fused with other data from AIS and from radar, which helps us have a less confusing image of what's around us. And also we can see further with the radar than we can with the cameras. We make a lot of use of weather data. So IBM owns a company called the Weather Company, which is the data company behind the Weather Channel. So we have highly accurate, every 15-minute weather forecasts on a 0.5 kilometer grid for the whole planet. And that's very useful to us. So we pre-process that weather forecast data in the IBM cloud and send it down over the satellite link to the AI captain so it can factor it into its considerations, so that it can navigate through the least bad weather systems on its journey. The rules-based system I talked about is another IBM product called Operational Decision Manager. And into that we've encoded the collision regulations. And they're done in a sort of English-like syntax. So it's not rules, it's not lines of computer code, but it's sort of an English-like syntax. So it's like a ship coming towards you to starboard, turns 5 degrees to port, then you should turn 5 degrees to starboard or something like that. So you can sit down with a sea captain, a ship captain, and say, does this rule make sense? And they can say, yeah, but maybe it should be 6 degrees, not 5 degrees. So you can manage the life cycle of these rule sets through the sort of life of the project, which greatly reduces the cost of implementation. And then we've got this optimizer that I mentioned. This is another IBM product called Cplex, which takes all the possible future outcomes, including things like constraints, such as how much battery power we've got, how much sunlight there's going to be left, where we want to go, what's around us, which direction they're going, and so on. And it says, right, the next best thing to do is to go over there. And then having made that decision, it then passes it to the operational decision manager to say, am I allowed to do this? And the operational decision manager says, well, you said go in front of that big oil tanker. Actually, you have to turn right, go behind it, and then turn left to safely and legally pass behind it. So the AI captain says, yep, okay, that's fair. And that's what it then does. And it keeps executing that until it reaches the next waypoint, and it keeps executing that on waypoints until it gets to the last one, which is its destination. So we give it a journey made up of a set of waypoints, and it's up to the AI captain to navigate safely between those waypoints. I mentioned that the ship is a platform for scientific research. We've working with a whole range of academic partners around the world. For the transatlantic crossing, we chose ocean chemistry and whale song to be the two main projects. So we had a project from IBM Research called Hypertaste, which is essentially an electronic tongue that licks the ocean every few minutes to see what it tastes like. This was actually a project that was designed for finding fake whiskey in a Scottish distillery. And it has a number of sensors, rather like our own tongue, for different chemical ions. And a machine learning model is trained to identify those different saturation speeds and therefore identify different chemical compounds. So that was bringing water into the body of the Hypertaste experiment, running it through the sensors and then flushing it out again. We have a number of sensors on the outside of the ship, things like conductivity, temperature, depth, salinity, pH, depth, or depth. So it's fairly standard sensors. They're the more robust ones. And then the ones that are more delicate, we bring water into the ship, run it through this little silver box with the blue bands around it, which we call the wet lab, and then pump it out back into the sea again. So that allows us to have the more sensitive experiments not being crashed into by the water all the time on the outside of the ship. As you can see, there isn't much room in there, but there doesn't need to be because there are no people on board, so it's all just very functional. We saw quite a lot of dolphins. So the other experiment we had was a hydrophone, which was recording audio from the outside of the ship all the time. And we had an experiment which we trained a temporal neural network on a catalogue of whale songs that we'd got from a whale conservancy charity. And so the idea was that we would listen out for whale songs in the audio and compare that with our catalogue of whale songs to see if we could spot any similarities. That's an ongoing project at Plymouth Marine Laboratory here in the UK, and some PhD students are currently wading through several terabytes of audio recordings to see if they can find anything. This is some pictures from dolphins who are hanging out with us. We saw quite a lot of dolphins, actually. They really like the low hum of the ship and very sort of sleek through the water, so they like to just play in front of the ship. We've got some lovely video of that happening. So the original plan was to go from Plymouth, UK to Plymouth, Massachusetts, reproducing the journey of the original Mayflower. We hoped to set out in 2020, which was the 400th anniversary, but because of COVID and other delays, we had the naming ceremony in 2020. Then by June 2021, we were ready to set off. The first journey only got to just west of Ireland, about here, before a mechanical fault meant that we had to turn around and go back again. It then took another year to get ready to go again, and so we went last April. And after a small diversion to the Azores, we actually ended up, because of a technical fault, not because of navigation. We had a fault with the computer, and we just went to the nearest land. So we ended up in Halifax, Nova Scotia, which was 3,500 mile journey. Very impressive. 32 days at sea. We had 8 days waiting in the Azores for a big storm to blow through. So we had actually crossed the Atlantic. We weren't where we intended to be, but we had crossed the Atlantic, so that was pretty cool. And technically we were in Canada, not North America, but hey. And then we went around the last 400 miles down to Plymouth, Massachusetts. And on 30th of June last year, 36 days at sea, nearly 4,000 miles, there's Mayflower autonomous ship moored next to Mayflower 2, which was the wooden replica that was built to commemorate one of the other anniversaries of the original Mayflower. And you can see the owner, Brett Fanner, very proudly sitting on the front of it, tying it up to a bollard there. So that was the very iconic photo that was in the Reuters press release. So where does this go now? So first of all, Mayflower is now based in Woods Hole Oceanographic Institute in Massachusetts. He's going to be operating out of there as part of the Twilight Zone project, which is exploring and cataloguing the flora and fauna of the ocean between 100 meters and 1,000 meters depth. She's going to be joining 3 crewed vessels this summer, so she'll be the 4th vessel doing sweeps of the ocean, cataloging the animals and the plant life using multi-beam sonar. We also very deliberately separated the AI captain from the Mayflower so that we can take it out and put it into other ships. And there's a lot of interest from commercial shipping and military and research ships for this AI captain technology, this full autonomy. When you say that you're intending to cross the Atlantic, that's one thing, but when you say you've successfully crossed the Atlantic, suddenly that changes the story and everybody wants to talk to you. So we've got a lot of conversations going on. We've got some trials underway with some commercial shipping lines. Obviously, it's going to be a very, very slow transition to autonomy. And in fact, it may never happen. It might be that you have an AI first officer on board the ship alongside the human captain, keeping an eye open, never distracted, never tired. You know, oh, there's an iceberg over there, Captain. Oh, thanks, I didn't see that. Hopefully avoiding the 90% of marine accidents are caused by human error. So hopefully we can reduce that problem. And a lot of interest from defence on autonomous fully autonomous ships for all sorts of applications, and also autonomous submarines as well, which the company that built Mayflower, M-Subs in the UK, also builds autonomous submarines, which the AI captain will be deployed into. So absolutely fascinating stuff. IBM's very proud to be sponsor of the Mayflower ship for the next 2 years. We've just renewed our sponsorship, so we get to keep our logo on the side. So we look forward to some exciting technology adventures. If you want to follow the story, mas400.com is the website. It's a little bit out of date at the moment. It needs some bit of tender loving care, but you'll be getting that in the next few months. And then if you want to buy a Mayflower t-shirt, we have a mass merch site where you can go and buy some Mayflower memorabilia. And if you want to contact me, I'm Andy SC on Twitter, or andysc@uk.ibm.com on email. Thank you very much. Very happy to answer your questions.
Okay, thank you very much, Andy. That's very good because we are the meat of the session and we are in time, so that's very good. Because we leave us time enough for the questions and answers. Well, we will go ahead with the next one. Next one will be done by Hernán de Frade. Hernán is a civil captain and doctor in law. He is teaching international law at the university and had a Fulbright scholarship at Berkeley University. He's working at the Spanish Merchant Navy Directorate, and actually is the manager of the safety and environment technical area for the Cantabric Sea. Is member of the European Community Autonomous Vessel Working Group and at the OMI Working Group, and he is the head of the working group of the autonomous vessel in Spain. He will be talking to us concerning the mascot and the initial development of an innovative regulation. Okay, Hernán, that's yours. Go ahead.
Thank you, Javier. Well, I'm trying to see where I can share my presentation. I can find a place. Oh, let me check.
You have just at the bottom, you have several icons, and you have one that says
I got it, yeah.
Okay.
Thank you. I got it. So, well, and just to put it on presentation mode. Sorry. Oh, yeah. Well, so here we go. I mean, can you see the presentation?
Yes.
Okay.
Yes, okay.
Thank you. Well, I will start yet. So, well, as you see, my presentation deals with the question of the MAS code, the Maritime Autonomous Surface Ships Code, and its initial development and the questions that bring it as really new innovative regulation. So it's so new. So, well, just going to the next slide. Oh yeah, here it is. Sorry. Well, so I mean, the questions I'm going to treat on this presentation is the first is related to the simultaneous development of the mass and the regulation. What are the uncertainties and new several aspects about the remote management, the absence of crew on board, the question of this is a recommendatory approach to regulation is going to be developed as a soft law question. And yes, in this regulation, there are a couple of premises just to be considered. The first is that the mass have to comply with the obligation of conventional ships, and also that the mass have to be at least as safe as a conventional ship. And also through these two premises, you can consider there is a technological challenge, but also a legal challenge. So, well, let's check here. Well, so just when we are going to check this question of the development of regulations, we can check it from three perspectives. The first is the IMO one, is a global perspective. The second is the European Commission as a regional level of development. And later, the internal law of the states, in this case is Spain, how do we deal with this issue? So, well, the first is just to consider what's the content and on the situation and all the things relative to the development of this code. The first is the regulation of the mass from a global perspective. And first is that IMO since 2018 has developed the regulatory scoping exercise, it's called RSE, and well, to check if the IMO conventions could be an obstacle or will hamper the use of mass. The outcome of this scoping exercise was bring that a lot of things shall to be clarified and defined before to go into the regulation. So, and also one question is to be considered is when developing this mass code is only intended for cargo ships, not for passengers, but at the moment. Yep. And how to put it on the IMO framework, just is intended to put inside the SOLAS convention, this mass code. And the development of the code is done by a specific correspondence group that has been organized by the Maritime Safety Committee of IMO. Yeah? This is the MSC mass correspondence group. This is the work where the work is being done. So this group has been created in May 2022. The Marshall Islands delegation is coordinating the work, and the objective is to prepare a draft code that could be applicable to autonomous ships. As I said before, it's going to be on a soft law basis. The outcome of this work correspondence group is to be bring up to the MSC 109 in a couple of years. And this correspondence group also reports to the Maritime Safety Committee and the joint working group on MSC Lake Fal. I said held this week, but actually less than 1 hour ago was still on the sessions debating a lot of interesting things that I'm gonna tell you on the next slide. I mean, there are a lot of states participating in this group. Mainly, it's for instance, Marshall Islands, the United States, Germany, also Liberia is working hard, China, Japan, and also Germany, Argentina, and for sure Spain. There are a lot of states working on these groups and made a lot of work on that. And just to deal with the massive task that the development of a code for autonomous ships is it has been spread on different groups, on different sections and functional requirements we're going to see later. And just the question is that there is a big internal debate, very enriching. There is a very interesting, but well, it takes a lot of work that take us for at least many meetings and many work to do at home. And it's well, but it's interesting at this moment. Well, what are the controversial issues I just said before? Well, the first is just to maintain the 4 degrees, the 4 levels of autonomy that were found in the regulatory scoping exercise. It's some ships with some assistance to navigation. Then level 2 will be ships controlled remotely but with crew. The level 3 will be uncrewed ships controlled remotely, and the level 4 plenty autonomous, fully autonomous, just being the ship itself who takes the decisions, linking with the previous presentation. Another thing is a debate is the question of what's a mass and what it means mass. For instance, at the beginning it was maritime autonomous surface ship, but now there is a strong trend to change it to maritime autonomous ships and systems. Also, another question about is really important is who is the master, and what happens if the master is not on board? And even so, if there is a computer that's managing the ship, in any case, at this moment of discussion of the joint working group, let's say that the master, that there will be a person responsible for all the operation. Could be the master, but in any case, there will be a person that feels the duties that international law put on the master of a ship. There was also a debate about the name of the remote station, about remote operation center versus remote control station, but remote operation center is winning. It's winning. It's just fresh from the open jet, because it has been said this morning. Also, a big issue that has been the main debate this afternoon in the work of this group is the question of the flag state jurisdiction over the remote control center. This is the question: what happens if the remote operation center is not on the territory of the flag state? It happens that the flag state shall exert an effective jurisdiction of this over the ship, and it's considered that the ship is controlled from any part, the flag state shall have effective jurisdiction over this place. So it's a big issue, and this afternoon, as I say, the discussion was related to this question. Other question interesting is just the remote operator or remote navigator, as we can call it, is a seafarer or not. It's also, it has its outcomes if it's considered a seafarer or not. Other question is the training of these operators, and for sure the matter of cybersecurity is in the center of any kind of remote control, and even the full autonomous question, for sure. Well, so what are the sections of this code? Well, these sections, as I said, well, this is intended to be finished by the second half of 2024, and this is a goal-based code based mostly on the experiences of the Polar Code, not defining requirements, but goals that shall be accomplished. Sorry, will be recommended, as I said before. And from this work, this first recommendatory version is expected to develop a mandatory version for 2028. But all the dates and the contents of the mass code are tentative, because everything is changing every day. Things that we have clear at the beginning of the work now are not so clear, and many other issues arise as well through all the process. While we're studying some subjects, new ideas come, and some ideas are here to stay yet. And well, the mass code is divided in 3 parts. There was a 4th, but on remote operation, but was removed. And now the 3 parts are general. The second part is principle of ships and autonomous function, and the most heavy part is the objectives, functional requirements, and provisions. So the first part includes an introduction related to the purpose of this part, the principles, the objectives to be kept in mind, verification and validation of all the application of this part, the structure of the code and relationship to all the IMO instruments, the terminology and definitions, a very important part, and the question about the certificate and survey. As we see, it follows the main trend of the rest of the IMO instruments. The second part, the main principle for mass and mass functions, it talks about the Western operational context, the safe states of the ship, the function required for mass, we will see on the next slide. The question of risk assessment, I'm going to put a small slide on this issue right now, and the system design principles, software standards, the question of communication, especially the connectivity and the human element. So this question of risk assessment is important just to know that the European Union, through the European Commission, made a proposal about how to deal with the risk assessment issue of the mass code. China has proposed to lead this part, but the European Union wants also to stay. So the European Union, not the European Union, but the states, the member states, as the European Union is not part of IMO, the European Commission is an observer, just endorsed a couple of documents regarding the use of the RBAT. We'll see later what it is. It's a tool on risk assessment developed in Europe by DNV for the European Maritime Safety Agency. This is the paper you see this just from the last month, and you see it's endorsed by all the European member states, the European Union member states. So the last part of the mass code is related to the goals, functional requirements, and provisions. This is the main part by my side. Well, the principles are important, of course, but it's where this different function, these functions, navigation, remote operations, communication, etc. These are here on the page, and just on you can see on the screen. It's important, but as how the mass should deal with these issues, they're not studying the whole thing, but how the masts are different of the conventional ships. It's only this part. As you see, there is a big task, and well, the different functional requirement sections have been passed to the states working on the correspondence group. In the case of Spain, we are dealing with the question of security, and also with the question of search and rescue that I coordinate. But have you seen, there are many other things, and I mean in Europe and the European Union, well, there's Sweden and Germany also in this issue, but it's interesting that many European Union countries are working on this issue. Just related to this question of the SAR section as an example of how it goes, well, in this section, Spain coordinates with the help of France. It's very collaborative. Also, the International Chamber of Shipping, the International Maritime Contractors Association, and the Comité International Radio Maritime, the International Committee on Radio Communications. And we have seen when developing this question that certain obligation under international law has to be considered, and we split in three parts. The general part, principles of action, for instance, is the duties of a ship to render assistance, the question of communications, and also the question of the rescue actions. Specifically, for instance, is thinking of SOLAS, for instance, going to chapter 3, chapter 4, chapter 5. Maybe there are many duties that have to be complied by any kind of ship. There was a revision version of this section and has been prepared and sent to the subgroup. It has been included in the document that has been sent to the NCCR subcommittee and will be subsequently submitted to MSC 107 that will be held by the end of May of this year. And well, what happens in the European Union? Well, I'm gonna be fast on this part, but I mean, I'm taking more time than I should have. Well, the European Commission has been very interested on developing the question of the RBAT, the RBAT, RBAT. It's down on the lower part of the screen. It's well, it's a software tool just to prepare risk assessments about the use of autonomous ships, and it's being developed by DNV, but also within the European Maritime Safety Agency. There have been many other questions related to the study of the contents of the training for a remote operator, and how the remote control centers could be, a remote operation center. Also, the question of the European Union just has been doing a bit of work, but mostly is related to the actions of the states and IMO, and just not to separate the things that are being doing at IMO. So, well, it's an intelligent point of view, and well, it's interesting just to check this initiative on the risk assessment. That is important. Well, and just to end, what's happened in Spain? Well, at this moment in Spain, we don't have, well, we have, I'll tell you later, not much regulation on this. We have an instrucción de servicio. It's mean not a kind of recommendatory for the administration on the procedures to follow, but it's not law by itself. But it deals with aspects about registration, flagging, qualification, and so. But I can say you that from the General Directorate, the Merchant Marine, we have been very close, paying close attention to what is going on at the international level, not only at IMO, but also at the European level. And we are working at this time very actively at the meetings of the IMO. And also at an internal level, is well known by Javier because he's a member from many years ago. We have established a national working group on 2020. We had already 8 meetings, and we have also organized from the ministry side a technical seminar on autonomous ships in October of the last year. And now I can say you that it entered into force the last week is as first in Spanish law. We have the first reference to the autonomous ships on our law, and it's on a negative sense. They are saying that any mass that want to enter the Spanish waters shall have an express specific authorization to do so. It's related to the safety of navigation and the risk that it may pose to the coastal state. And on the national working group of autonomous ships, we are really proud of this part of development in Spain. We have seen we have a lot of members from many sides. Now we are more than 60 members. It's interesting. The Aine and Coin are both really truly active members, and there are many members of these associations working at the working group. The meetings of the group, the national group, are 3 per year. We are expecting to have the next meeting on the 1st of June. The last meeting was on February 17, and we expect that the fall meeting will be presential again. Don't know still where it is going to be held, but it's interesting. And the opinion of this group is really important, not only at the internal level, but also that give us ideas to take to the IMO, or to the international fora. So, well, conclusions. Well, it's a complicated task, this question of regulating the autonomous ships. The mass code only deals with aspects of ships of autonomous ships that can be different of the conventional ships and affected by the different degrees of autonomy. Now there's a debate about the degree of autonomy versus the mode of operation. There is a good collaboration among the states. The results may vary from the initial thoughts that we have at the beginning of the process. Just to finish, it's just to say it's a real moment of innovation in international law. So everybody is really expectant to see what's going on this. So, well, thank you very much. And just stay here for any question that you may pose. Thank you.
Okay, thank you very much, Hernán. has been very interesting. And well, we are arriving to the last one that will be held by Rocío Malpartida. Rocío is industrial engineer and is working for UTEC as systems engineer. She is expert in non-crewed vehicles and works on the integration of different systems in autonomous vessels. She is part of the researchers in different European funded projects, mainly for defense. Well, she is going to talk us about the high reliability on the USB for niche applications. Okay, Rocío, you are muted. Okay, thank you. Bye.
Thank you very much, Javier, for such a warm welcome. And thank you, Aine, for having us once again. Well, let me share my screen, first of all. Are you able to see the screen now?
Yes. Okay.
Okay.
Thank you.
So, first of all, I would like to introduce a bit of our company for those who don't know us, our capabilities. Then I will speak about the developments that we carry out for these niche applications in which we see that the USVs are really helpful. And finally, I will speak about the operations in which USVs have been proven to be really, really useful and helpful. So first of all, we are Unmanned Technologies Applications, UTEC, and we were founded in 2016. We are specialized in the development of unmanned surface vehicles, although we are expanding and we are developing other unmanned vehicles, such as aerial and underwater. Our facilities are in Madrid, both our offices and our workshop. And our sailing tests, we usually carry them out in Cartagena, in Vigo, or in Pantano de San Juan, which is a lake in the north of Madrid. Our main capabilities are regarding systems engineering, electronic and mechanical design, mainly we are proprietary of all of our designs and all of our electronics. We develop the software, which is also proprietary. We design the communication system for the vehicles. Of course, we integrate all of the systems, and we test and carry out real life operations. So our developments in this sense have 5 key features. 2 of them are really close and related because we develop flexible and modular solutions which allow us to develop multi-purpose unmanned systems. These systems are provided with advanced capabilities, and given the redundancy in several systems, we provide high reliability in the operation. Of course, since we develop unmanned vessels, the maintenance has to be low because there's nobody on board. In the sense of the high reliability and safety, and in line with what Hernan said about the 2 pillars of the unmanned vessels, we base our developments in 4 main aspects. We believe that the unmanned systems are a huge advance in decreasing the accidents due to human error. As Andy mentioned, those are close to 90%. So we believe that by using unmanned systems and autonomous systems, we can reduce that human error probability. The endurance of these boats is higher because since there's nobody on board, we can use them for longer periods of time at sea without the con of having someone to get on and off because the shift is ending, or tiredness of the crew. Another very important pillar, as Hernan also mentioned, is the cybersecurity. We believe that every development has to have a high cybersecurity resilience, and we provide all of the developments with encrypted communications and, if needed, encryption units on board. Finally, as I already mentioned, we also have redundant subsystems on board to ensure that in case of failure or any malfunction, there's some system that is able to handle the vehicle. So now to the focus of the presentations, which are the niche applications that we have identified over the years that we have been manufacturing USVs. Well, these are the first can be, it's really straightforward because it's in terms of surveillance, which is usually a repetitive task, and sometimes when someone is surveilling an area can become tired. So with the unmanned vessels, surveillance becomes easier, and mainly in coast areas, port surveillance, any area which needs continuous monitoring at from the ashore center, but also in the sea. It is also really important for inspection, since this is mainly related to surveillance, but inspection becomes mainly in infrastructure, whenever there's a defect in an infrastructure, inspection through USV in the water, in ports, or mainly critical structures, it's interesting. In addition, there's areas in which underwater threats become especially important, because mainly in civil applications, we can see that sometimes divers enter areas in which they are not supposed to be in. So with a USV in the sea, these underwater threats can be detected early, and the person or any other object is detected, and there can be a warning sent to the person or a support unit. Another application, and in relation with what Andy mentioned about the underwater life, is the bathymetry applications. There are some areas in which knowing what the seafloor looks like, it's really important. And again, this is a routine task, and sometimes automating this process reduces the cost of the operation. So a USV can be a really good asset in this application. Regarding logistic support, we believe that although the portuary authorities are still researching and getting to know the autonomous vessels, we believe that these smaller ships can be used as a logistic support in many tasks, such as escort operations outside the port for bigger vessels, or maybe in order to be able to transport any goods or anything that a bigger vessel needs without the need of it entering a port. Another application also in relation what Andy mentioned about the use that the Mayflower is going to have, it's the environmental control. Through different sensors, a USV can control the different sea life below the surface, as well as the water quality and the environment quality, the air quality, and it can gather weather information. And again, these are routinary tasks, and with a USV, the cost of the task can be significantly reduced. Of course, the defense application is always the first to come to mind when we are talking about the new technologies, which the unmanned vessels are becoming highly popular. But in defense, we can see that all of the mentioned above can be applied also to the defense field. The USVs can also be used for search and rescue applications in order to be used as a fast response vessel. And last but not least, we believe that we can use the USVs for any type of marine research, which involves large periods of time at sea, which also involves a higher cost of personnel. So in this sense, and having identified this whole range of applications, we believe that our solutions are provided in a customized way. In this sense, we are able to integrate many sensors, many payloads, and any equipment for navigation needed. In addition, our systems are provided with the vessel, and we also provide the ground control station, which is also designed as the customer needs. So how we believe that these applications should be targeted. We believe that through an engineering process, by knowing the application, we can know the customer needs and we can develop the system requirements. By having the user requirements, we can know what requirements our system needs. Once we have those requirements, we come up with the design. What we do is we work with shipyards, which are the manufacturers for the boat, and we consult on the vessel design and suggest modifications in order to integrate our system. Regarding the application, we select and integrate the different payloads that are needed for carrying out its intended mission. We also integrate the unmanned capabilities. And we, as I mentioned, design the ground control station with the different screens, different human computer interfaces, which are most suitable for the final customer. Finally, we do the performance testing. Once we have integrated everything in the vessel, we do the performance testing, and we validate all the requirements that the system had in the first place. So I would like to talk about the projects that we have carried out and that we have we have used for different operations. Our first project was the prototype project, which we developed around 2017, and it's called the Kaluga. This vessel, it's a rib, a 6.7 long rib, and we have integrated many sensors, but the most important is the camera for surveillance. It's a long range detection camera. We have also integrated a radar, and we integrated an RWS in order to provide a defense application. In this sense, this is the most multi-purpose USV that we have right now, and is the one that is having all the innovations and having the sensor integration. In addition, it has its own ground control station with our own mission planning system, and the sensor view application. Our mission planning system, it's carried out through waypoints as the one from Mayflower, and we can say that the level of autonomy of this rig, it's between 3 and 4, depending on from which point of view you see it. We are implementing the collision avoidance system, and of course once the mission is ongoing, you can see on the screen how it's going on, and if there's an object, you can see the situational awareness as well. So, the second project that we developed is regarding one of the environmental control with unmanned vessels. And we developed this project with Blocan, the oceanic platform of the Canary Islands. And the main purpose of this 6.7 meter long rib is to carry out environmental control in the area of the research facility in which is it. So we have integrated a surveillance camera It has also a weather station, a water quality sensor, and it has also a robotic arm, which you can see in this picture, but it has it integrated, which allows the use of an ROV or any other sensor that needs to go underwater. We also developed its own ground control station and a special communication system for the Blocan, which needed different requirements that the ones we are used to having. This is one of our latest projects with the Kunai vessel, and this is a huge step because this is the first USV that the Spanish Army has acquired. We gave it to them in November, and they have it in Cartagena. And this project, it's one project that tries to show the capabilities of having a swarm of different unmanned vehicles, because this USV is provided with a launch and recovery system in which a UUV is mounted and deployed whenever needed for underwater threat detection. In addition, since this was for defense, we were required to integrate a speaker and a horn in order to provide acoustic warnings whenever a threat or an unauthorized access was detected. For this purpose, in the ground control station, a microphone was also integrated, and also in the USV, there's a microphone as well to have the situational awareness and to be aware if there's any sound to support the surveillance operations of the ship. Again, we have its own proprietary control station and with its communication system, and of course with the appropriate level of encryption and level of redundancy, as I mentioned before. Last but not least, in the list of civil applications, we are developing the SCUBA project, which is a project for spill control. We are aware that in the environmental control and testing, these spills are really important and sometimes difficult to manage. So in this sense, we are developing a USV which is able, through a surveillance camera, to detect where an oil spill is in the sea, through two sweeping arms in the front of the ship, gather it, and through some skimmers, put it into a waste tank installed in the USV. Again, this project has also its own ground control station and its own communication system. Again, this as you can see, we are mainly focused for now in 6.7 meter long ribs, because we believe that whenever you're trying to develop a product and a project, sometimes small is better in order to grow. So our next projects will be of bigger vessels. Now I would like to speak about how we have operated and how these systems have performed in the different aspects. Many of these operations have been carried out in the context of NATO exercises, but as I mentioned, we have the ECUVE project has been operating in Canarias for several years now. We integrated ourselves with Telefónica network during the Picasso. We used the Sinbad demonstration, and we also perform the NATO exercises, as I said. So I'm gonna speak about the different NATO exercises in which I've participated up till now. In September of 2021, the Army decided to try and demonstrate the different capabilities for manned systems in maritime situational awareness, surveillance, escort of vessels. And we were invited to participate along with other companies, and we were able to operate through long periods of time. And we integrated ourselves in different operation systems. In 2022.
Sorry, 5 minutes.
Yes.
Okay.
I'm finishing.
Okay.
I'm finishing. Sorry.
Okay.
In 2022, we demonstrated our capabilities in the dynamic messenger, which the aim was to try and demonstrate the interoperability with combat systems, and we were able to integrate ourselves with the Audaz system. We were the first to operate during night hours through the integration in the system in the BAM. Last but not least, this year there are two different operations in which we are going to participate: the Flotex 2023, which is a demonstration of the capabilities of the Spanish Army, and in the Dynamic Messenger of 2023 as well, in September. Finally, to summarize, I would like to outline the main points that we believe that we are a company with a vast experience in USV development and operations, providing highly reliable solutions with advanced capabilities. Our systems have proven to be a great support in different operations. All of our systems are always optionally piloted vehicles, just in case there's a need for someone on board. Our systems are custom and adapted to the user requirements, and we always develop. We have developed the systems for the niche applications that I explained above. Thank you very much, and sorry if I extended myself.
Okay, thank you very much, Rocío. I think we have finished just in time. So in that sense, has been very successful. So we are going ahead with the questions and answers. So we have received some questions. So I will start with, well, the first question has been sent from Lars Andrea. And the first question is for Hernán, and says, will IMO consider to include also requirements to systems such as automatic mooring and shore-based sensor systems that the autonomous ship may be dependent on?
Well, these questions of maneuvering is not bad carried by Spain, but I can say you that this question of maneuvers is considered. There has been so many developments by, at least in the Scandinavian countries. I mean, especially in Norway, but also in Finland. I mean, it's very typical. It's an interesting question because, well, it's a typical matter of debate because it's one of the points where the autonomous ships may rely on specific mooring arrangements or something like that. But at this moment, I mean, yes, because, well, if there is this is a third degree or a fourth degree mass, it will be necessary to moor without at least from the ship side, to moor without persons on board. So it's going to be taken into account.
Okay, thank you, Hernán. Well, next question is also for you. To what extent do you believe that there will be stringent requirements to available communication lines between the ship and remote control center? And this question is linked to another one that says, do we need to anticipate loss of communication with the autonomous ship?
Well, at the first consideration about the autonomous ships was to take them to the second degree or the third degree, just to control the ships remotely. But what is a question that Andy Stanford Clark just mentioned before is the question of being autonomous, because at some parts there is no good communication. It's mainly one problem that the latency and the lack of communication, of the loss of signal, may imply to the effective control of the ship. So for this quest is solutions, mixed solutions with artificial intelligence may be considered, because the connections with the remote operations center is really difficult. There have been been developed many systems. First is the Starlink by Tesla, but I mean, it's gonna be interesting on this issue just to broadband and have a good communication system, but also a question on other low orbit satellites just to bring some good communication. It's a very important issue. It also happens at the risk assessment. We also consider the question of what happens in the loss of signal or the loss of the lack of control by the ship. Shall remain on the same place, shall go to another safe place, or whatever. It's interesting.
If I could just add a comment about Mayflower, our original design point was that it would not be continuously connected, and that if we got connectivity, it would be kind of a luxury. So that made it very clear to us that it was human on the loop, not human in the loop. And it was quite late in the program that Iridium came on board, and we have full 400 kilobits satellite link, so we could stream the webcams. But that was completely unexpected and certainly not the design point. So you're absolutely right. You cannot depend on having reliable communications far out at sea. So you have to design for that.
Okay, thank you. Well, next question is to Andy. Can the Mayflower project contribute with experiences for remote and autonomous control that could provide important input to the IMO process on the mascot?
Yeah, so I mean, we work very closely with the IMO and the MCA and lawyers and insurers, because part of the kind of the pioneering work for autonomous ships is to bring the whole industry with you. So it's not just convincing people that autonomy can be made to work or that it's safe or whatever, but it's getting the certifications in place. And we had a huge argument with the MCA about certification, and in the end they agreed that if we had an escort within 12 nautical miles, that would be okay. So we could run autonomously close to shore, but it had to have an escort with somebody with a big red button to kind of stop it if necessary. But also we actually in the end recertified Mayflower as a US craft rather than a UK one, and as a leisure craft rather than as a working boat. And if you do that, then you can do whatever you like, in fact. Because it was very painful, and I think the MCA and the IMO would, well, we get the impression that they think that if they go slowly enough, then autonomy will go away. It won't happen. But of course, it is going to happen, and it is happening. So they're going to have to drag themselves out of the 20th century and join the 21st century.
Okay. Also for you, Andy, is automatic collision avoidance algorithms versus the need for intervention by remote operators in complex traffic situations are highly debated. What is your experience on this from the Mayflower project?
So luckily we did have the Iridium satellite, so we could see what was going on, and we left the system on AI Captain autonomy for as long as possible. In the busy shipping lanes off the southwest coast of England, it was quite stressful, but it actually coped fine. And the multi-vessel collision avoidance, the whole thing, the big advantage of being at sea is you've got much bigger distances and much slower speeds. If I was doing autonomous cars, I'd be I would not be doing this. It'd be far too stressful. You're having to read road signs at 60 miles an hour and avoid a child with a football running in front of you. No thanks. But with a ship, we have this sort of Maslow's hierarchy of needs, and rule 1 is don't hit anything, and rule 2 is if in doubt, see rule 1. So if the Mayflower comes across a situation it can't deal with, it'll stop, wait, and reassess 30 seconds later to see if it's got any better. Sometimes it'll even turn around, turn around and go back the way it came, and then kind of turn around again to see if it looks any better the second time. Because there's no kind of, you can't pick up the phone and say help, I don't know what to do, and hand it back to us, because it may not have connectivity. So it has to know what to do in all situations. So stopping and waiting is always an option.
Okay, well, next question is for Rocío. Can reduced size USBs be used to generate a sufficient training data set that can be used to train machine learning or artificial intelligence algorithms that has sufficient coverage for formal approval processes with coastal or flag state authorities?
Yes, of course. I mean, the expertise and knowledge generated by the operating this kind of small ships can be, of course, transferred to the operation in higher ships and provide useful information on how these manage different types of situation and how safe and the operation and extendable it can be. So my answer would be yes, of course. It would be really useful indeed.
Okay, and also there is another question for you, Rocío. What is your experience with loss of communication, for example, cyber attacks, or how to handle this remotely?
Well, there are many, let's say, situations in which we can lose communication. First of all, it depends on the type of communication we are using. We can use the satellite communication, which Andy mentioned, through the iridium antennas, and that is useful when you're at open sea, and there can be loss of communication or mainly loss of payload information, since the data rate and the band is quite narrow in order to have good information on high resolution of the cameras. The other type of communication, which is the most common, is the line of sight, which is carried out through two antennas, which they see each other. So this communication, in terms of reliability, is reliable until you lose like the sight of the other antenna. So what happens if you're on shore and you have your vessel and a cargo container, and a cargo ship goes through the middle, so you lose line of sight and you are not able to operate. In this sense, what we do is we program the vessel to do something, like depending on the situation. If it's a really congested area with a lot of traffic vessels, we program it to stop until we have again communication. It sits still until we are able to safely operate it again. In whenever there's no such congestion, the vessel can operate through the collision avoidance system in a safe way. Oh, I believe Cesar would like to add something. Cesar Martinez is our CEO. If we could, please.
Okay.
Good afternoon. Yes, good afternoon, everyone. Thank you. Just to complement what Rocío was saying. In fact, the way we solve this problem, because usually we have redundant system for communications. So we have a narrow band link and a broadband link. So we use one of them to send all telemetries gathered on board. And we also use this for control the boat. So usually we lost the first link. I mean, the one with the information related with the telemetries on board telemetries. And this is, let's say, a flag. Say, okay, we are near the limit of the coverage. So in a few minutes, we are going to lose totally the control. So in fact, we never experience a total loss of control. Because of that, we have redundant system, 2 links at least, and always one of them was lost first. And this is a flag that we are going to lose the second one. So that's the idea, to have redundant system to avoid loss of control during navigation.
Okay, thank you, Cesar. Another question for Andy. What is the biggest technical challenge that Mayflower faces?
So what we found actually was that the 2 problems that were the 3 faults that we had with Mayflower were nothing to do with the computers, nothing to do with the software. They're all to do with stupid little mechanical problems. In the first mission, an exhaust hose fractured and exhaust gases went into the hold, which then got sucked into the generator and choked the generator. Second time, an electrical switch failed. The problem is, by not having any people at all there, not even an engineer, someone who can just fix, someone with a roll of gaffer tape who can just tape things up, you're completely at the mercy of just any little thing failing, and you can't make everything completely redundant. So if you read sci-fi books, then they always have like an R2-D2 mech droid who can go and fix things, or there's like nanoparticles that can go out and fix holes in the hull. There's always some little robot thing that can go and fix problems, and that's what we're missing on board Mayflower. So if one little thing fails, we're completely stuffed. So that was the biggest technical problem we faced, was hoping that nothing silly would, like a screw coming out or a pipe failing.
Okay, thank you. Well, there are some questions that are for everybody, so maybe any of you can answer. There are 2 that are linked. One says that the level 4 means that a mass is intelligent, and then it is safe to navigate with an unmanned boat. Okay,
I'll go first. So level 4 autonomy does not mean intelligent in the sense that we do. I mean, it doesn't really know what's going on. It is just following rules or making things up, interpreting situational awareness in a very narrow field. It can't play chess, it can't write you a sonnet. So it's not intelligent in the way that we would normally think of intelligence. And although we have default rules, like you were just saying, stop and wait and look around, it can't do really intelligent planning of, oh, maybe I should go completely in the opposite direction and make up a creative idea. So no, not intelligent in the normal sense. And what was the second part? Is autonomous navigation safe? Question mark.
Yeah.
Well, again, if you obey rule 1 to the letter, i.e. don't hit anything, then yes. But if you do have to hit something, if you can be going so slowly that it doesn't actually cause any damage, then that's also a good thing. But you could probably turn it around and say, is human navigation safe? Because a lot of accidents, most accidents are caused by human error. So, and I think we face this with autonomous cars as well. As soon as the first autonomous car has an accident, everyone's going, oh, autonomous cars are terrible, they should be stopped, they shouldn't be allowed. well, there are thousands of human accidents in cars every day caused by stupid humans. Not even stupid humans, very intelligent humans in unfortunate situations. So, and we don't jump up and down and say, oh, we should ban all cars from being driven by humans. So I think it's a matter of degree, and what we really have to do is build trust by doing these experiments and demonstrating in accumulated hours, thousands of hours of autonomous navigation, that the accident rate is very, very low. And use that to continuously improve the software when you have near misses. One of the benefits of the Mayflower system is that because we've got this rules-based system for the collision regulations, we have explainable AI, so we can explain exactly why it made a particular decision, which if we're debugging it or having to justify to somebody why it took a decision it did, then we've got the printout to show it.
Okay.
I'd like to add to the Yes, I'd like to add to Andy's statement regarding safety. I believe there are two ways of looking at it. The safety part regarding cybersecurity and the effectiveness in collision avoidance and how it behaves autonomously, and the security aspects in terms of what happens if someone goes on board. Is it able, because there's nobody to protect the vessel itself? So am I going to lose control? Is that person going to use my boat as a weapon? So I believe we should distinguish those two parts. The first part, it's perfectly covered with what Andy said, and the second part, I believe that we should make a reflection and think about which applications and in which terms it's really useful to have an uncrewed vessel, a completely empty vessel of people, but with cargo, or I don't know, a fast boat. So in which terms is it useful, or is it going to be more of a problem? So maybe we should think about where is it really useful to take out people from the equation.
I think this is a very curious approach, because I never thought about this, to have an unmanned vessel that is just stolen by somebody that goes on board. Okay. And well, there is another question for Andy. Tell us about the next chapter in the Mayflower story.
Sure, yeah. So as I think I mentioned, Mayflower's based at Whole Oceanographic Institute. She's going to be doing sweeps of the ocean on the Twilight Zone project, using the multi-beam sonar. We've also got a project which we're working on, not quite sure when it's going to be implemented yet, listening out for whales with trackers on them. Some of them have tracker beacons, and we're going to put a receiver on the Mayflower so that if she hears one of these trackers, if she can request from the AI captain to say, can I go and look over there? This is the first time we've had an experiment kind of making a request to the AI captain to change the mission, to deviate from the primary mission to go somewhere else. And that leads into a really interesting situation. Imagine you have two experiments, one wants to go over here, one wants to go over there. How does the AI captain prioritize which one to do? Perhaps you have like an eBay auction. You can pay Bitcoin to the AI captain to say, well, mine's worth 3 Bitcoin, and the other says mine's worth 4 Bitcoin, and you get into a bidding war, and then whoever wins the auction has their experiment run. It gets into some really interesting situations, but at the moment, the AI captain can tell the experiments whether they can run or not, but they can't. There's no feedback from the experiments to the AI captain. So this is going to be the first adventure in that area.
Okay, thank you. Well, I think we are right into the last question that I think that is also for everybody, is what is the most relevant aspect on the mass code?
What was the last word?
What is, sorry, what is the most relevant aspect of the mass code?
Well, there are many issues. So you can consider from many different points. But I mean, the question of remote control or the autonomous control is the most innovative. Is the core of the mass code, and also the change of perspective. Just having ships without crew or even ships controlled remotely. It's a change. It's a main change. So you know that the maritime sailing, the navigation world is very conservative. This issue is interesting because, well, it may bring some changes. It will not be immediately, for sure, but in the future we will be prepared just for these issues. And I mean, it's a question that everybody looks a bit at, and they say, it will pass, it will not happen, but well, it will pass, it will pass. And so stay prepared. It's not going to be tomorrow, for sure. Going to take a lot of development, but it will pass. Keep in mind that many things will change.
Absolutely, yeah. So I think I agree. It's a cultural, the biggest obstacle is the cultural change with regulation and legal and insurance. And the technology, I think we'll get there. I mean, multi-ship avoidance is a hard problem, but you know, it's being solved. Factoring in the weather is a key thing as well, because obviously small boats in big waves are quite at risk. But I think it's getting people to accept the technology and the safety of it. That's going to be the biggest obstacle.
Okay.
To pass the question to Lars Andreas, he will have a different perspective, I mean, from the side of operation.
Well, I think that if we look to this mass code development, then first of all, what I hope is an outcome is that we get some sort of a common language to discuss what an autonomous ship is, so that we continue to kind of focus on the practical issues and not necessarily the wordings and so on. So that would be a very good outcome for me. The second is that I believe that these autonomy levels perhaps are not as useful as generally perceived now. Because if we look at them, then it's some sort of graduated automation capability, together with whether or not the vessel is crewed or uncrewed. But what the developments in the mass code now is trying to do is to make us assess which functions are to be controlled by automation. Okay, am I over? Yeah. Which functions that are to be controlled by automation together with humans, and for which conditions. I think that's a very good step in order to be able to assess and say something with substance on what, for example, an autonomous cargo ship can do and cannot do.
Yep.
Okay.
I believe that one of the, sorry, Javier.
No, go ahead.
I believe that one of the most important points of developing the mass code and having an existing regulation is regarding what Andy was saying before about the reluctancy of people towards a failure in an autonomous or automatic system. So it seems that whenever something is regulated, it tends to soothe people and to make them feel that there's someone looking over the technology and the development. So I believe it's a really positive development.
Okay, thank you. So we are arriving to the last question that says if is it enough developments on ships and harbors to be adapted to unmanned ships?
Can you say that again, please?
Yeah. Is it enough developments on ships and harbors to be adapted for unmanned ships?
Yeah, very good question. Well, yeah, ideally, yeah, but in reality, no. So, you know, you've got 100 years of legacy. Maria, can you go on mute, please? 100 years of legacy behind us. So we are going to have to design these autonomous ships to deal with the infrastructure that we have.
It's important. I mean, also from a practical question you have been checking here in Spain is the question of not more for regular or merchant vessels. The problem will be, for instance, the interaction with the pilots and the entrance into port is a real new question that should be tackled, but it's difficult to deal with.
Okay, well, I think we have arrived to the end. I think I will thank you very much to the speakers and also to all the attendants for this session. And I will give back to Diego for the closing of this session. Okay.
Thank you, Javier. Thank you, Lars, Andy, Rocío, and Hernan. Thank you really for your explanation and explaining which are the projects and the status of the project that you are driving now. So also thank you for the people that has been attending. I think that it has been very, very interesting, and I'm sure that probably in the future we will have another chance to reconnect. Thank you very much.
Thank you, everybody, and good night.
Thank you. Bye-bye.
Thank you. Bye-bye.
Bye-bye.